Good afternoon, everyone. Hope you're all having a great day. My name is Charles. I'm here with Francine, a geologist.
Hello.
And today we are on to our second installment of 12 of our webinar series addressing geology and the mining sector. Today specifically, we're going to explore rocks and minerals. Once again, if you have any questions during this presentation, just type them in the chat box on the right of your screen. I'll write them down and we'll address these questions at the end of the webinar. And moreover, if you stay until the end, you'll get to interact directly with Francine if you want to turn your microphone on and ask some specific questions or just exchange with our specialist. You'll have the opportunity to do so. Aside from that, the first installment, Introduction to Geology, is now available on our YouTube channel. So just search for IDDPNQL or FNQLSDI on YouTube. You can find it pretty easily. And without further ado, I'll leave the floor to Francine, and we'll learn more about rocks and minerals.
Thank you. Welcome to my second lesson, rocks and minerals. So there's going to be some parts of lesson 1 that we're going to go through more in detail. So rocks and minerals is going to be separated in 2 hours. The first hour is going to be the types of rocks, and the second hour is going to talk more about minerals. So type of rocks, we're going to check the 3 kind of rocks: intrusive, volcanic, sedimentary, igneous, sedimentary, and metamorphic. Igneous with the intrusive and volcanic rocks, and for the minerals, we'll go through the classification and the general composition. So types of rocks. First, what is a rock? The simplest definition I found was rocks are solid masses classified into 3 fundamental different types: igneous rocks, sedimentary rocks, and metamorphic rocks. So what you need to remember is that igneous rocks are the primary rocks, that meaning that all rocks come from igneous rocks. These rocks can then be contributors to what we call secondary rocks, so sedimentary and or metamorphic rocks. So igneous rocks, general description, they're known as primary rocks, and they're known as mother of all rocks. So they're the oldest types of rocks. They're formed at depths within the earth. What you'll learn from this lesson is every time I say something is formed at depth, you have to remember that a rock forming at depth means it's slowly solidifies itself and it is below the Earth's surface. These can be later exposed by erosion. Igneous rocks are formed from magma, and they form into a variety of rock types. Magma, just to go back from lesson 1, what is magma? Magma is essentially molten rock made by the partial melting of rocks within the Earth's interior, and it undergoes these melting episodes under different conditions of high temperature and high pressure. Rock melts. When rock melts, it becomes less dense and it rises automatically towards the Earth's surface. Magma that reaches the Earth's surface is called lava. So here, just to retake lesson 1, magma is formed in depth, lava is formed in subsurface or surface. This, we'll see in this lesson, has a big impact on the rock's texture, mainly to differentiate between volcanic and intrusive rocks. So igneous rocks can be separated into 2 groups: extrusive versus intrusive, or volcanic versus plutonic. So extrusive or volcanic are igneous rocks forming at the surface of the Earth. Perfect example would be a basalt. We're going to start with the intrusive or plutonic. So intrusive or plutonic are igneous rocks that formed in depth, and so cools over long periods of time. They've developed larger crystals, and their textures uh, is represented by larger crystals. A good example would be the common granite. This is the types of rocks that we have seen on the geological map of Quebec. So the colors, the main colors here, simplified geological map, is basically shown here on the right. All the intrusive rocks are represented within the pastel pinkish colors. The volcanic rocks are represented into the greenish tints. Sedimentary are blue, and the metamorphic rocks are the light and darkest yellows. If we zoom in within the southern half portion of Quebec, province of Quebec, we see the distribution of these rocks. So as we've seen the geological provinces of Quebec during the first lesson, we can see that the St. Lawrence platform is mainly sedimentary rocks. The Hudson Bay platform is sedimentary rocks. The Grenville province is mainly composed of either metamorphic rocks or intrusive. You have some small patches of volcanics and sediments throughout. Within the Superior province, you have mainly within the Abitibi sub-province the volcano-sedimentary rocks, so basically volcanic and sediments. You also have some intrusions dispersed through the volcanic belt, and you have some metamorphic rocks. So the most common igneous rocks within the province of Quebec are shown here. So you have the impactite, the granite, granodiorite, syenite, tonalite, and the within the mafic group, the anorthosite, gabbro, and diorite, and the pyroxenite. We'll see the difference later on during this lesson between the felsic, intermediate, and mafic subdivisions of these rocks. So the most common being the granite is an igneous rock. It is also known as a felsic rock. Felsic because of its color. We'll see that later on. Granites are mainly composed of quartz or silica, being the lighter portion, and it also has a lower concentration of darker minerals, which are micas, and we'll see them later on. So granites are mainly pink, red, gray, or whitish, and they form with slow crystallization of magma below the surface, and that means we'll see the grains with the eyes. We don't need to look at them under the microscope. The cyanide is the intermediate version of igneous rocks. So it is between the felsic and a mafic rock, cyanides being intermediate. So they too solidify slowly within the crust. So they have a similar solidification process as granites. Composition are basically the same as granite, but they have their major difference is the absence or very low quantity of quartz and darker shades than granite. Like granite, we can see that we see their grain sizes. The gabbro is the common mafic igneous rock within Quebec. It has the same composition as basalt. The only difference is, again, the coarse grains. So as we can see here, the grains are big enough for us to see. Their shades vary between greenish and black, greenish gray to black colors. I'm gonna add, there's a new participant. So if we move on, for the volcanic rocks, they're formed from lava from a volcanic eruption. We also have a subdivision within the volcanic rocks that is called volcanoclastic or tuffs. So there are rocks and sediments that create from magma erupted into the air. So they are technically sedimentary rocks, and they are formed from the clastics. So clastic meaning fragments. Here is an example of a rhyolitic tuff formed during an explosion. So we can clearly see the clasts or the fragments within them. We can see their shapes being angular, and we can see a matrix. So that's basically what forms a tuff. It's a rock consolidated from any kinds of erupted material within a finer matrix. So the distribution of the volcanic rocks within the southern portion of the province of Quebec, everywhere where you see a green color. The main volcanic rocks in Quebec are from Felsic to Mafic to ultramafic are rhyolite, dacite, basalt, andesite, and comatite. Here is an example of a rhyolite. So rhyolites are extrusive igneous felsic rocks. They have a high content of silica or quartz that is very well presented in their color, pinkish or gray in color. And being a volcanic rock, you remember that their grains are difficult to observe by the eye because they were cooled down more rapidly and formed near the surface. So that's the basic difference between a rhyolite and a granite. If we move on to the basalt being the equivalent in composition to the gabbro, we can both, you can see here that it's a mafic rock. Basalt can also be found under the intrusive dike condition. They have a greenish gray to black in color, and as you can see here, they're very fine grained, so we can't see the grains with the eye. Moving on to the ultramac, here is an example of a comatite. They're rock derived from extremely hot magma. They have rapid cooling of the hot lava flows, creates their spinifex typical texture for comatites, as we can see here. The comatites are rich in magnesium and very low content of silica, potassium, and aluminum. So we're moving on to the sedimentary rocks. Sedimentary rocks being secondary rocks because they are formed from the accumulation of small pieces of pre-existing rocks. So pre-existing rocks, their parent rock is an igneous rocks. Sedimentary rock is formed through the deposition and consolidation and solidification of sediments transported by fluids, as we saw in lesson 1. So either by water from rivers, lakes, and oceans, by ice, by glacier, and by wind. So sedimentary rocks are separated into two, subdivided. Either there's two types. They're either based on the source of the sediments. So they're either formed by solid particles from weathered rocks. So these are called detritus particles. So good examples for them are sandstone. Sandstone are formed by particles of sand from other rocks. And shale. Shale is formed by other particles, which is mud. The second type is the chemical sedimentary rocks. They are formed from dissolved material. So these dissolved material are transported by the water. So example from lakes and oceans, example here is the limestone. the calcite is precipitated mainly by the evaporation process. Sedimentary rocks are also formed from erosional processes, as we saw in lesson 1. So these erosional processes grind down rocks, pre-existing rocks, into fragments and into smaller individual mineral grains. This material is transported and sorted by fluids naturally, so the coarser and finer fractions are naturally separated by density. The sedimentary rocks deposition are mainly deposited in layers and frequently contains fossils like plants and animals remains. So studies of sedimentary deposits show that to reveal characteristics from their depositional environments at the time that the primary material was accumulated. This information can help in defining the history of the geological events and climate change of an area. So here we see both types of sedimentary rocks. On the left, we have the detrital sedimentary rocks, which are made out of solid particles. On the right, we have the chemical and biochemical sedimentary rocks that are mainly made from chemical reactions. So detrital sedimentary rocks, the main ones we can see are shales, sandstones, breccias, and conglomerate. As you can see, the first thing that we see within shale is that they have clay-sized particles, very, very fine grains. They are fissile, so we can see distinctive layers. The sandstones, the fragments are a bit larger, and they're composed mainly of sand-sized rock fragments. So these could include quartz, feldspar, and clay. The breccias are basically formed from a mixture of fragments from angular to subangular fragments of rocks that underwent brecciation. And conglomerate are poorly sorted mixture of rocks fragments, including rounded or sub-rounded pebbles. So that's the main difference here. The limestones are created mainly from calcite crystals. We have fossiliferous limestones, which contain fossils, either animal or plants, and we have oolitic limestone. Oolitic limestones contain mainly aggregates of oolites, which are smaller spherical calcium concretions. And finally, we have chert and rock salts. This is just to show, to go back a bit, to do a link with lesson 1. So to have the origin of the sediments as seen as the stream gravel, and from the beach and sand gravel, moved by ice, wind, and water. We have these once they have deposited, either in 2 layers, as seen in the middle picture within the sandstone and the shale, and either solidified as conglomerates. So these include all the fragments that were transported, and the chert on the left. So if we go on the map of Quebec, again, to see the distribution of these sedimentary rocks. The main sedimentary rocks in Quebec are the Waki, mud rock, ardoise, and shale, the sandstone, the limestone and dolomites, the conglomerates, and the iron formations. So if we look at them more closely, here is an example of a shale sample. So as we can see, the grain is very fine, and we can see that these grains were deposited into layers. These break into thin pieces with sharp edges. Shells have all kinds of colors depending on their original material. So they vary from red, brown, green, gray, and black. The sandstone has particles of mineral, rock, or organic material reduced to sand-sized grains. So that's why we see the grains here more closely than within shales. These sand-sized grains are created or deposited from weathering and transport from their depositional site by the action of moving water, wind, or ice. The color of the sandstones can vary a lot, again, from whitish to grayish to pinkish, depending on the material forming it. The limestones here basically forms into clear, warm, shallow marine waters. They are known as organic rock because they are usually composed of shell, coral, algal, and fecal debris, and they result by the precipitation of calcium carbonate from lake or ocean waters. And finally, the conglomerates, as seen here. The difference here, as we've seen volcanic tuff before, here we can see that the fragments are subangular to angular versus the tuff, which is here they are sub-rounded to rounded, contrary to tuffs, which are subangular to angular. So we can see the matrix also between the clasts is called matrix, and it is always smaller particles and contains mainly calcite and quartz that binds the rock together, binds the fragments of the conglomerate together. Here is a good example of a bended iron. Bending irons are chemical reactions combining iron and oxygen in marine fresh waters. The most important iron oxides are hematite and magnetite, which are formed from iron and oxygen. Metamorphic rocks are like sedimentary rocks. They are secondary rocks because they are formed from various parent rocks, either igneous and sedimentary rocks, and even from metamorphic rocks. So any kind of rocks can form a metamorphic rock. Metamorphic rock is mainly related to everything that has to do with metamorphosis. So anything meaning a change in form. These rocks underwent changes either like mineralogical, chemical, structural. They adjust the solid rocks to physical and chemical conditions imposed at depth below the surface. So any event that can change a rock, mainly from temperatures to change in pressures. So types of changes that can cause a rock to be unstable and therefore to change and therefore become a metamorphic rock are mainly related to environmental changes causing the rock to be unstable. So example here would be a rock which is deeply buried under tons of earth and exposed to increased temperature and pressure, would transform itself to slate, from slate to marble. Metamorphism typically occurs below superficial zones where processes of sedimentation, compaction, and cementation takes place. Metamorphism occurs where a rock is subjected to conditions unlike those in which it was originally formed. So basically, is anything that changes from when the rock was originally formed. Examples here of a metamorphic rock that once one form of rock has changed to another form either under the influence of heat, pressure, or fluids without passing through a liquid phase. So The important thing is to remember is these changes are undergone without the rock being melted. So we have an example here of the Metamorphic, a Igneous and a schist, and a serpentinite. So this is a great picture to understand these changes, how a rock can go through a shale state to a slate to a fillet, a schist, and an Igneous. So basically, it's just a question of increasing metamorphism. So again, they're created by physical or chemical alterations of once igneous or sedimentary rocks, metamorphosed by intense heat or pressure within the crust. Here is a table showing on the left, we have the increasing from the top to the bottom, increasing of temperature and pressure, and the increasing of the foliation within the rock. Foliation, we'll see that in lesson 3. It's a structural deformation of the rock. As we can see here, we're going through the protolith is the initial rock, and its metamorphic equivalent once it was changed through the changing of temperature and pressure. So we go from a sedimentary shale to a slate, where we can see the layers, where they can be along their known cleavage or their known weakness, structural weakness within the rock. A shell can also be pushed forward to a phyllite. So again, meaning the fragile cleavage is wrinkled and almost folded, and it has a higher deformation than the slate. If we move on with higher deformation, the shell can also become a schist. So here, the schist or the schistose is taking the pattern of the foliation. As the rock is being transformed, there is lineament or preferential alignment of the minerals within the rocks. And finally, the shale or the igneous rock is at higher increasing temperatures and pressures transformed into a Igneous. On the right side, we see some metamorphic rocks which are not foliated. Example of a sandstone or a siltstone which is transformed to a quartzite, and a limestone which is finally transformed to a marble. So the distribution of the metamorphic rocks within the province of Quebec, as you can see, major part of the Grenville sub-province is mainly composed of metamorphic rocks and some intrusive rocks with a little volcanic and sediments. And we also have metamorphic rocks within the Abitibi sub-province here on the southwestern side of the province, of the Superior Province, and within the middle northern part of the Superior Province. The main metamorphic rocks in the province of Quebec are the granite igneous, which is basically granite that underwent some changes with temperature and pressure to become igneous. We have tonalite igneous, coming from a tonalitic rock, and a migmatite, which has a higher pressure and temperature changes, internal change. And these are originating from the protolith, which is an igneous rock, versus a protolith, which is a sedimentary rock. So we would have a paragnous and we would have a marble. Paragnous coming from sandstones and a marble coming from limestone. So just showing a resume of them, we have the most common in Quebec are the quartzite, the slates, the marbles, the gneiss, the schist, and the serpentinite. So now we're moving on with the types of rocks, how to be able to differentiate them either with a sample size or on the field. So we're going to start with their composition and texture. So intrusive igneous rocks, they form in the naturally insulated settings. So as said before, these rocks are poor conductors of heat, being formed at depth. Their minerals crystallize slowly, and they form large visible crystals. Versus the extrusive igneous rocks, which are formed by rapidly cooling magmas or lava near the surface or subsurface. The minerals crystallize quickly, so preventing large visible crystals from forming. And the formation of very fine grained crystals are not visible to the naked eye. So that's the big difference once on the field that can be used. So this is just a recall from lesson 1, where we see the distribution within the earth and on the surface, how these rocks are being formed and their origin. So we have the magma chambers showing here the stocks or the dikes, which are the vertical or vertical, cutting through the horizontal layers. We have the sills, which are horizontal dikes cutting through or laid parallel to the horizontal layers. And we have on the surface all the events that can create depositions, volcanoes, cinders, the lavas, the stocks, and so on. Good example of an extrusive rock, as we can see here about St. Helens, a picture from the USGS. So when you see all these material being ejected from a volcano, all these material can be used later on to form new rocks. Here is the what we call the balance reaction series. The balance reaction series will show how the rocks are formed from higher temperature to low temperature cooling magmas. So going from deep depth to the surface subsurface. It also shows what we have another subdivision for decomposition within intrusive and extrusive rocks, where we talk about felsic, intermediate, mafic, and ultramafic rocks. So what does that mean? So within either the intrusive and the extrusive rocks, when we talk about felsic, we talk about rocks that are very rich in quartz, micas, and K feldspar, K for potassium, feldspar. It also has to do with the color, and we'll talk about it a little later on during the lesson. When we talk about intermediate rocks, either for intrusive and extrusive, so example diorite and andesite, they contain a very low percentage of quartz, mica, what we call the felsic micas, and the K feldspar, and they contain a higher percentage of what we call mafic micas, which is biotite, and sodium-rich feldspar. If we move on to the mafic rocks, equivalent to gabbro or basalt, we have a mix of amphibolite, pyroxene, and a mix of sodium-rich to calcium-rich feldspar. And finally, the ultramafic subdivision, example of peridotite and komatiite for intrusive and extrusive rocks. We have a mix of olivine, pyroxene, and calcium-rich feldspar. And this diagram, if you switch it around, remember that this is going from depth to surface, so from higher temperature to lower temperature. From higher temperature to lower temperature, the magma is cooling. From depth to surface, we're moving on from ultramafic, mafic, intermediate, and felsic. So that too is an example of criteria that we can use to know exactly within the earth where the rock once formed or crystallized. So if we take the Bowen series and we check real rock samples, as mentioned here, we can see also that these are subdivided now into two other divisions based on their texture. What we saw before was on composition. Now on texture, when you're on the field, composition, yes, you can see some of these minerals, but sometimes they're hard to recognize. You can also use their texture. So the texture between the intrusive and extrusive rocks are basically between phaneritic and aphanitic textures. So what I did here is I put examples for each felsic, intermediate, mafic, and ultramafic. I put examples of samples so you can recall their difference. Phaneritic meaning that you can see grain size, as we've seen so far, and aphanitic is that the grain size is small, so it is very hard to see with the eye. So if we go from depth to surface, for the ultramafic, we have the peridotite for the intrusive example versus the comatite for the extrusive example. Moving on to mafic, the gabbro and the basalt have basically the same composition. It's just within their texture that there's a difference between phaneritic and aphanitic. So grain size visible, grain size not visible. Then we move on to gabbro, and it's equivalent to, we move on to diogite, and it's equivalent to andesite. So again, we can clearly see the grain size here versus no grain size here. And finally, for the felsic rocks, which are in the subsurface, you can see the phaneritic texture versus the aphanitic texture. If we look at it more closely, we can see here same composition. Same, if you send this to the lab, you would have the same composition between the two, the same analysis between the two. The only difference is their texture. Texture being here, granite, so phaneritic texture, larger crystals, aphanitic, very fine crystals. Grain size here are large enough to be distinguished with the eye, versus here on the right for the rhyolite, cannot be seen within the naked eye. The rocks with the phaneritic texture, as said so far, are textures that are from intrusive rocks, are magma, which has been formed underground and cools and crystallizes very slowly, allowing the crystals to form or to take shape, versus magma here on the right, which has been formed from lava and very quickly, so the crystals don't have time to form completely within a larger shape. The other element that can be used to differentiate between the felsic, intermediate, mafic, and ultramafic rocks are what we call the M.Sc.A, or the Mafic color index. And this is mainly done by eye test, nothing really difficult there. Is we just look at the percentage of mafic meaning dark colored minerals that we can see. So mafic dark color minerals include all the grays, blacks, or greenish colored minerals. So when we say that a rock is felsic, it contains less than 15% dark colored minerals. So the M.Sc.A is under 15%. An intermediate rock is between 16 and 45%. Mafic rock is between 46 and 85%. And finally, ultramafic rock is higher than 86%. Of course, that will vary from one individual to another. So it is a rapid index, but it's a good way on the field to differentiate between felsic, intermediate, mafic, and ultramafic rocks. So this is an example of these, of the first three, so the felsic, intermediate, and mafic. As you can see, just by color, here it's very well shown. You can see that the clearer one is the rhyolite, the darkest one is the basalt, and the in-between one, or intermediate one, is the andesite. So we have felsic rhyolites, the intermediate andesite, and the mafic basalt. So within the simplified geology of Quebec, the intrusive rocks and the volcanic rocks, as shown here, there are subdivisions: felsic, intermediate, mafic, and ultramafic, which is all based on the M.Sc.A or the mafic color index, going from the lowest percentage to the highest percentage. And this table here will resume what we just saw. So within the extrusive and intrusive, the intrusive and the extrusive rocks, the intrusive and volcanic rocks, the phaneritic texture versus the aphanitic texture, so the visible crystals versus the no visible crystals, the slow cooling plutonic rocks versus the fast cooling volcanic rocks, and their composition, whether they're felsic, intermediate, or mafic, as shown here, and their equivalents. So we have the granite versus the rhyolite, the diorite versus the andesite, and the gabbro versus the basalt. We can also add two extra easy compositions that we can see on the field: the porphyritic meaning that they are visible crystals in basalt or andesite, and they are very large crystals in granite. So if they are visible in basalt and andesite, you can imagine how big they are in granite. And finally, for the glacis, just to say that they have like a dense glass look, like vitreous look. A good example would be a black obsidian, black volcanic rock. And they have a glass froth that is light or intermediate in color, like pumice. So far I've shown examples of sample size rocks. So we're going to go on the field now. So since we have a virtual barrier, I'm going to bring you on the field to see these rocks. So what we've seen so far, the intrusive versus extrusive rocks and their equivalents. So the granite with the rhyolite, basically both felsic rocks, and basically composed mainly of low temperature minerals, meaning subsurface quartz, micas, and feldspar. The granite on the left side, they show what we call a crystalline coarse grain. They're light colored, and that's it. That's all I can say. What else? Granite is very abundant in the mountains ranges in North America, in the Rocky Mountain and the Canadian Shield. On the right, we have the rhyolite, which is a pale felsic fine grain volcanic, and it has the same composition as granite, and is common in continental volcanic regions, and it's just, again, a question of grain size. If we move on the field with an example of the intermediate rocks, so they refer to rocks that are in between felsic and mafic. They tend to be pale to medium gray in color. So we have examples here for an intrusive rock, which would be a granodiorite, and an extrusive rock, which would be a dacite. Granodiorite is a coarse-grained plutonic igneous rock with mainly just quartz and plagioclase. And a dacite is an extrusive volcanic rock with an aphanitic to porphyritic texture, with an intermediate composition between andesite and rhyolite, so the percentage of dark minerals. Finally, for the mafic rocks, we have here on the left side the intrusive rock gabbro, and on the right side the extrusive rock basalt. So basically the same composition between the two. The only difference between the two would be their grain size. So the videos will come back later. So if we go back to lesson 1, when we saw the rock cycle, the simplified version of the rock cycle, maybe we can understand it better now, understanding that the igneous rocks being the primary rocks to all rocks, formed by plutonism, magma. So the intrusive version would be the granite, diorite, and gabbro. And the volcanic rocks would be the rhyolite, andesite, and basalts. All these igneous rocks undergoing weathering and erosion events would then create all kinds of sediments: gravel, sand, silt, mud, clay, lime, and soil. These sediments would then be deposited, would be compacted and cemented to create all kinds of sedimentary rocks, as we've seen, the main ones being the conglomerate, sandstone, mudstone, siltstone, shale, greywacke, limestone, the chert, the chips, and the salt, and the coals. And all these rocks within the process, within all the events, would also create what we call the metamorphic rocks. So the metamorphic rocks, the main ones, either from sedimentary protolith or from igneous rocks protolith, a combination of slate, argillite, schist, gneiss, marble, metasandstone, quartzite, greenstone, serpentinite, and the metachert. So all these now are what we see within the mineral dissolution, mineral precipitation, and it's an ongoing process. So if we take each of these processes a little bit farther now, what we can see is that the igneous rocks from the cooling of molten material and are rich in silicate minerals. We'll talk about them later on during the lesson. So the molten material is derived from depths within the earth. Typically, they are enriched in iron and magnesium silicates, and they form what we call from the mafic and ultramafic rocks. The magma and lava, which is associated mainly with the continental crustal regions, are enriched more with felsic silicate minerals and are rich in silicon and aluminum, like the feldspars. For the weathering of the rocks, mainly what we have to retain is the water. Water, very important here for what we call the universal solvent. So it will dissolve and transport material in different solutions. It will alter the chemical composition of the mineral, and it will also be the agent for transporting sediment erosion and deposition. So not all rocks and minerals behave the same way. What you have to remember is that hard and durable minerals like quartz, they tend to resist weathering and erosion. So they will be transported long distances and carried as sediments by flowing water or wind instead of being dissolved. Example here of the quartz. Quartz hardness, as we will see the table later on, is very high. On the Mohs hardness scale, it's 7 on 10. So it explains also why it is extremely abundant mineral on the earth, since it cannot be destroyed. The quartz-rich rocks, they weather and erode. They tend to break down or decay into finer clay, whereas quartz grains tend to endure the abrasive processes while being transported. So that's a thing to remember. The finer clay materials, they get carried away by water or wind. The larger ones, the quartz grains, they concentrate and they form quartz-rich sands. like on the beaches and the sand dunes. The minerals in the sedimentary rocks, quartz, calcite, and some iron and clay minerals. Minerals with high hardness and low solubility are transported by erosion and deposited into sedimentary basins. The soft minerals are highly soluble and dissolved and carried by surface and groundwater, where most contributes to saltiness of the seawater. So the dissolved components in water can precipitate to form what we call the mineral cements, including the calcite, the iron-rich minerals, so either hematite and limonite, and the silica, which is rich in quartz. Finally, the iron mineral content in rocks are mostly responsible for the earth tone colors. So when you move around and you see colors, we'll see them later on. Finally, to explain some metamorphic processes here, mainly thing to remember is the changes in heat, pressure, and exposure to fluids over time. These will always change the mineral composition, and they will convert the sediments into sedimentary rocks and change the sedimentary and igneous primary rocks into metamorphic rocks. These rocks, if they are themselves exposed to fluids like water and air at or near the surface, they will also be degraded rocks to form several kinds of sediments. So this is the rock cycle. This is the best image you can find that details all the concepts we've seen so far between lesson 1 and lesson 2. I won't go through each and every one of them, but what you can see, what I like about it is that you have all the different kinds of rocks listed and their emplacement within the earth, where they are formed, within the depth of the earth versus the surface, whatever structural event can cause them to change, and either weathering, erosion, transportation, how these particles are changed under deposition, compaction, and how all these rocks once created, either the intrusive igneous rocks versus the volcanic igneous rocks, the sediments and their compaction, deposition, etc., near the surface, underwater, and how all of them are changed to become the metamorphic rocks, either by higher pressures, higher temperatures, and how they are put back within the system. So this is the best image to keep in mind. So now we're going to move on to the minerals. One big mistake that people do is that they mix between a mineral and a rock. So the best way to explain the two is that a mineral is what constitutes a rock. A rock, to be a rock needs to have a minimum of 2 minerals. A mineral is just a constituent of a rock. A rock is like a box that contains several minerals. So a mineral is a natural occurring inorganic solid with a definite internal arrangement. So it has a crystal structure. And these, we won't cover them all today. This is like a complete other course. But it is the base on how we recognize minerals on their crystal structure. Earth has a lot of minerals, like over 4,000, but about 1 to 2 dozen of the common minerals are the ones we'll see today, the most important ones. And we also have the minerals that we consider like gems, which are very rare. So here on the right side, I've included like the most important ones or the most common ones that we get to see. So we'll go through them mainly through when we'll talk through on how we recognize them during the rest of the lesson. So, good image also to understand mineral versus rock. So as we see here in the middle part, minerals, so one mineral, quartz is one mineral, feldspar is a mineral, micas, orthoclase, and so on is one mineral, versus rocks. So rocks, as we've seen them, igneous, sedimentary, metamorphic. So a granite versus a sandstone versus igneous has different composition. These different compositions is different compositions in minerals. So several types of minerals, like a granite, would be composed of quartz, feldspar, and micas. So it has like the basic 3 minerals to compose one granite rock, and so on. So the thing to remember is that a rock is a composition of several minerals. So the big difference here, a rock is a hard, naturally formed aggregate of minerals, so several minerals. So it's a mixture of one or more minerals, but basically more than 2, I would say. Rocks are what makes up the materials of the solid earth, and the word stone is just another common term used to describe a rock. So we have several ways in classifying minerals. We're going to start first, basic one, from low to high temperature minerals. So same thing as we mentioned from low to high temperature rocks. We have the same process of differentiation with the minerals. So again, low temperature minerals, we have what we call quartz and muscovite, and as the temperature rises, we tend towards more mafic material, or minerals, sorry. We have also a typical metamorphic minerals. So typical metamorphic minerals that has formed or were created under metamorphism. And these metamorphism minerals show us the increase of temperature and pressure. So the main ones are talc, chlorite, epidote, garnet, actinolite, serpentine, chrysotile as vistas, the stolonite, and the corundum. They're the main ones that we can see. And then we move, for mineral identification, we move to simple tests. So the first one is the hardness or durability property. So these tests are done to be able to evaluate either the physical or the chemical property of a mineral. So for the hardness, hardness is based on a mineral chemistry and crystal structure. And as we'll see, is that the different mineral families will have a different Mohs relative hardness scale. So the hardness scale is defined by the Mohs scale. It's from 1 to 10, 1 being the most soft, to 10 being the most hard, the hardest one. So the simple mineral samples are scratching tests with items or materials of known hardness, which can give a general range of hardness on the specimen. So if we move from talc, both talc and gypsum can be scrapable by the fingernail. The fingernail is known to have a hardness of about 2.5, so it would be in between here. So talc, since we are able to scratch talc and gypsum, we know that they're under 2.5. Calcite is scratchable with the 1 cent copper coin. The fluorite and both the fluorite and the apatite can be scratched either by a nail or by a steel knife blade. When we move on the Mohs relative hardness scale, the orthoclase is scratched by a steel file, and scratch the glass. Sorry about that. I'll retake that. The orthoclase, which has a Mohs hardness of 6, can be scratched by a steel file, but itself can scratch the glass. So arriving here around Mohs 6, it's either way. It's what we can scratch the mineral with, or what the mineral can scratch, if that makes sense. So quartz, if we move on, quartz a hardness of 7, it scratches window glass. So here we don't scratch quartz, but we scratch window glass with quartz. The topaz can scratch glass. It's hard to say. Finally, the corundum, which has a Mohs hardness of 9, scratches both glass and topaz, and the diamond scratches glass and corundum. So, what are these mainly used for? Basically, a talc for talcum powder. Gypsum is the main ingredient in plaster. Calcite is the main ingredient in cement. Fluorite is known within toothpaste. Apatite is found within minerals, the main minerals in our bones. Both orthoclase, the K feldspar, K for potassium, and quartz are found within glass. Topaz is a known gemstone, and the corundum is known for the rubies and sapphires, and the diamond finally for jewelry and industrial uses. When we move on to another test, simple test that can be done is the magnetism. So magnets stick mainly for iron minerals. So common mineral rich in iron is the magnetite. The other minerals that show weak magnetic attraction, including iron-rich metals, are the hematite, goethite, chromite, craquelite, pyrrhotite, and siderite. The color test. Color tests here are very important. Hematite is mainly known to be reddish, but you have also gray, black types of hematite. The composition doesn't change. And you also have the limonite. Limonite is just an orange to brownish mineral, which shows hydrated ferric oxides, and it just shows the rust on iron, which is known as limonite, which is the oxidation of the iron. Magnetite here, example of iron oxide minerals. This is a grayish black magnetic mineral. And then the last one there, the pyrite, which is a brass colored mineral, is an iron sulfur. And it's one of the most important sulfur dioxide, iron sulfur within the world. The streak color test is very important. The example here is pyrite. We know that hematite gives a red streak. Examples, the main examples. Pyrite is brownish to greenish, and the magnetite is black. This is shown as a good example, as here we see one of the big mistakes that is made is between magnetite and hematite. People tend to think that the sample on the left would be magnetite because of its color, but we do have black hematite, which is known as spicular. And if we do the streak color test, we can see that the line is red. So that even if the hematite mineral has varied colors, its streak test will always be a red, rust red streak line. So that's a good way to differentiate it. What is used is unglazed white porcelain tile to do the streak color. So that's easy to bring on the field. Example here of the pyrite, which is a dark brownish with a tinge of green. Another simple test is the fizzing reaction. We always carry little bottles of mild acid, which is called HCl, and these are mainly used to differentiate calcitic minerals, which are highly reactive to HCl, and it's an easy way to differentiate them between calcite, dolomite, and kerite, and so on. Dolomite fizzes to acid, but it has to be warmer and hotter temperature acids. If we move on to other physical and chemical properties evaluation, malleability. Malleability just means metals that can be hammered to create new objects. So the main example ones are the gold, copper, iron, and silver ones. Elasticity. Elasticity meaning that the mineral is soft and bendable. So most minerals, they fracture or shatter when put under stress or shock, but minerals like mica, they have a high elasticity, so they are soft and they can bend instead of breaking. So here is a table where I did a table for you that resumes all of the physical and chemical properties that can be done. On the left side are the ones that can be observed, versus on the right side are the ones that can be tested easily, but they require equipment. So the observable ones, the main characteristics are the crystal shapes, their colors, their cleavage, their luster, like metallic versus non-metallic, their diaphanity, the way that, meaning the way that the light is reflected on the object, so it is either transparent, translucid, or opaque. Their refraction, their striations, the feel of the mineral, their odor, like main example would be sulfur. It smells like rotten eggs, and their taste. The simple tests that can be done requiring equipment would be their hardness, as we saw the table before, the magnetism, the streak, the acid reactions, whether the minerals are fluorescent or thermoluminescent minerals, their malleability, elasticity, their density, and finally the phosphorescence and the radioactivity. Another way to classify minerals is to separate them into two main classes, non-metallic versus metallic. So if we start with the metallic are the ones that can be subdivided into two, either ferrous versus non-ferrous. Ferrous meaning contains iron versus non-ferrous have no iron. And the non-metallic minerals can be subdivided into four categories: chemical industry, building materials, fertilizers, and the fuels. I've done a little summary table to differentiate both the metallic and non-metallic minerals. First, their meaning. So easy. Again, the metallic minerals are the ones that contain raw form metals in their chemical formula, versus the non-metallic, which have no metal elements in their chemical formula. So that's the easy part. Metallic minerals can be found either into igneous and metamorphic rocks, versus the non-metallic minerals, which is found into sedimentary rocks. That's by the sensu stricto definition. Nowadays, metallic minerals can also be found within sedimentary rocks within certain types of environments. New products also. Metallic minerals, they are extracted by melting metallic minerals. so you can create a new product, versus non-metallic minerals. We cannot yield new products and metals if melted. Another good difference between both is for heat and electricity. So metallic minerals are good conductors of heat and electricity, versus non-metallic minerals, which are good insulators of heat and electricity. These we'll see further on, within another lesson coming later on. The malleability and ductility. So metallic minerals are both malleable and ductile and hard, so they do not break, versus the non-metallic minerals, which are not malleable and not ductile, and so they're soft and they can break. And finally, their luster. Metallic minerals have metallic lusters versus non-lustrous non-metallic minerals. A list here of the main ones for the non-metallic minerals, mainly composed of chemical elements like the limestones, the dolomite, talc, quartz, mica, clay, silica, and gemstones, construction stones, industrial, and the coal. For the metallic chemical elements, we have separated them with their metallic content. So for iron, we have pyrite, pyrrhotite, magnetite, hematite. We have gold, which is gold alone. And then for copper, we have chalcopyrite. For zinc, we have sphalerite. And for galena, we have, for lead, we have galena. Other ways to separate from non-metallic to metallic if we use a luster. Luster is just a word to say how a mineral reflects light. So the first thing to observe in a mineral, is it bright? Is it dull? Is it metallic? Does it have a metallic look? Is it vitreous? So we have some examples here. At the top, we have the metallic lusters of the copper, the silver, the gold, and the iron. For non-metallic lusters, we have several categories. So we have the ones that are more pearly, vitreous, like glassy type, the resinous, the silky ones, the greasy ones, adamantine, the dull, and the waxy kind of look. We're going to start now with the non-metallic minerals within the silicates family. So the silicates family, we're going to start with the felsic ones, the quartz. Quartz being a very hard mineral. It is colorless or a white mineral. Anytime you see crystals of quartz which have other colors than colorless or white, it's just that it has impurities. You can see that the quartz has a glassy texture, and it's very common in all kinds of rocks, in the igneous, metamorphic, and the sedimentary rocks. Here are other types of quartz that you can have, and you can have them into other kind of spaces like geologs, which within rock fissures, and they can also be found as semi-precious gems, and these can be included within the amethyst, citrine, quartz, rose quartz, and the smoky quartz. Smoky quartz is just natural irradiation of aluminum-bearing material. Smoky quartz is often found associated to gold-rich veins in Abitibi. The silicates, again, for the felsic quartz, but this time the type of quartz associated to sedimentary rocks are mainly chert, jasper, flint, agate, and chalcedony. Here is a picture of chert. Chert has been quarried through time, through history, for all kinds of stone tools, weapons, and other daily and ceremonial usages throughout history. So it has been a very important mineral. If we move on to the non-metallic silicates with feldspars within Felsic rocks, the orthoclase. So the orthoclase is a rock-forming mineral, a very important rock-forming mineral, which is also known as aluminosilicate. Alumino meaning rich in aluminum. So it is colorless or pale colored, and orthoclase is potassium rich. So it is also known as a K-spar, K for potassium, and it is mainly associated to felsic rocks. From now on, I put on the slide also physical properties tables for each, where you have all their main characteristics from hardness to specific gravity, streak color, their own color, and their luster. So if we move on to other feldspar within felsic rocks, we also have the P.Geo class, which is also aluminosilicate, so rich in aluminum. And here it is the sodium Na, sodium-rich type, which is known as the albite, and it is also associated to the felsic rocks. To the differentiation between albite and the anoctite is that the anoctite is the silicate feldspar for mafic rocks. So it is calcium-rich instead of sodium-rich. So rich in aluminum, calcium, and this one being associated to mafic rocks, it means it forms at higher temperatures than the sodium-rich P.Geo class. And finally, we have the mafic silicates. So the mafic silicates are known as ferromagnesium being ferro for rich, ferro for iron rich, and magnesium for magnesium. So example here is the olivine, which is principally made out of magnesium, iron, silica, and oxygen. It is mainly associated to igneous and metamorphic rocks, example within basalt and peridotic rocks. The pyroxene is another ferromagnesium silicate. So it is a mafic silicate because of the ferromagnesium, so dark colored. It is iron rich, magnesium rich. The only difference here is that the extra from the silica and the aluminum, it also has chrome, cobalt, manganese, titanium, vanadium, and scandium. The crystal has prismatic crystal habitus. The amphibolite is another mafic silicate, another ferromagnesium typical silicate. So again, iron rich, magnesium rich, and this time it varies between calcium, sodium, and aluminum. And the amphibolite is mainly associated to metamorphic rocks. Here is an example of the hornblende, which has like fibrous or columnar style crystals. If we move on to the silicates, the micas family, so if we start from felsic, the felsic micas silicates are known as the muscovite. We have the example here. So muscovite is silicates minerals that have a sheet-like crystal arrangement that allow them to cleave into thin sheets, as we can see here. The silver gray form of the mica is like a platy sheet that are like overlying each other, and they occur in both igneous and metamorphic rocks. The mica silicates, but for the mafic version, are the best one is known as biotite. So same thing, the biotite is formed as a sheet-like crystal arrangement, and here it is, since it is mafic, as we've seen before, it is darker, so black, dark brown, or dark green sheets that can create flakes. And it is an important composition of igneous and metamorphic rocks. So if we move on to the metallic minerals now, we're going to start with the gold of all gold. So the composition is Au. Gold is, as we can see here on this picture, is often found within gold-bearing quartz veins. We have the hardness of gold here, which is pretty low, which you can see that it is very soft. It's 2.5 to 3. I said that before that our fingernails are 2.5, so we can chip up gold with our fingernails. The color, to remember, color of the gold is golden yellow. We can have whiter golds. The whiter golds is just gold associated with silver, and the streak will always be yellow. So the P.Geo is an iron sulfide. It is the most abundant sulfide in the world. It is constituted of iron and sulfide, and sulfurs. P.Geo is cubic, crystal isometric cubic minerals, mainly brass yellow, and the color can be tarnished because of the iron that can oxidize. The streak color of P.Geo is mainly greenish black to brownish black. So, and the hardness is between 6 to 6.5. So we cannot chip it with our fingernails. So I did this table to differentiate between gold and pyrite, which is a true history, which has been known as fool's gold. People have often mistaken both P.Geo for gold. So main color, P.Geo is mainly brass yellow versus gold, which is always a golden yellow. P.Geo is brittle and will break under pressure. Gold is very soft, as we saw, 2.5 to 3, so it will bend or dent under pressure. The streak color of P.Geo will always be a greenish black versus gold will always be a yellowish streak. The gravity gold is very much denser and higher gravity than P.Geo. And finally, the P.Geo metal luster is there, but it tarnishes to a dull brass because of the oxidation of the iron, and gold will never tarnish. So if we move on to the to the copper iron sulfide, the main one is chalcopyrite. So it's composed of copper, iron, and sulfur. Hardness is between 3.5 and 4, and it is a brass yellow. It tarnishes to gray, green, and sometimes it becomes iridescent. The sphalerite is the main example for the zinc, iron, plus or minus iron, sometimes not, there is or there's not, sulfide. And it is a perfect example for dodecahedral perfect crystals, so it has like 6 directions. Their hardness is a bit lower than medium, so it's between 3.5 to 4. The color varies a lot. Sphalerite has a color that can vary a lot, and that's one element that people mistaken a lot. So it can vary from yellow, brown, black, red, green, white, and colorless. And the streak varies too, so that doesn't help. It varies from white to yellowish brown. And the thing to differentiate it between any other minerals that have a white to brown to yellowish brown streak is its odor. It has a sulfur odor or a rotten egg odor. The galena is our lead sulfide, so it's PBS. As we can see, it has cubic crystals like pyrite, except the color. Color is not the same. The streak color is lead gray to black, and the color of the mineral is more like a bright silver than versus a brass yellow from the pyrite. So it's an easy way to differentiate between the two. Also, the hardness of galena is very low. It's 2.5, so it can be scratched by fingernail versus pyrite, which is higher, which is 6 to 6.5, which is not scrapable fingernails. Finally, for the iron oxide, as you can see here, is magnetite, so iron and oxygen. Highly magnetic, as we can see the picture up there. So the streak is black versus hematite, which is red. The Mohs hardness is between 5 to 6.5, and the main color is black to silvery gray. Hematite, same thing. Hematite has a varying color from black to gray to red, but the streak will always be red. So we're gonna move on to the 4 videos to resume what we just saw, and then we'll move on to live questions if there's any.
Scientists are always looking for ways to put things into categories, and rocks are no exception. Rocks are solid masses occurring naturally as part of our planet. As it turns out, rocks can be put into 3 fundamentally different types: igneous, sedimentary, and metamorphic rock. This lesson will identify and describe these 3 types of rocks. Let's start with the igneous rock. Igneous rocks, for example basalt and granite, are crystalline solids that form directly from cooling magma. Alright, that's fine, but what is magma and what is its source? Magma is molten rock made by the partial melting of rocks in the Earth's interior under conditions of high temperature and high pressure. As rock melts, it becomes less dense and rises towards the Earth's surface. Magma that reaches the Earth's surface is called lava. Most lava flows are quiet, but some can be violent, such as the eruption of Mount St. Helens back in 1980. Igneous rock that forms at the surface of the Earth is referred to as extrusive or volcanic rock. These are named after the fire god Vulcan. Basalt is a good example of extrusive igneous rock. Igneous rock formed before it reaches the Earth's surface is named intrusive or plutonic, after the god of the lower world, Pluto. These rocks cool over long periods of time and thus develop large crystal structures, as we see in granite. Some intrusive rocks are subsequently exposed to the surface, but only after uplifting or erosion of the Earth's surface. Otherwise, they would remain buried. While igneous rocks make up the bulk of the Earth's crust, they're often covered by relatively thin sheets of sedimentary rock. As the name suggests, sedimentary rock is formed from sediments or debris transported by liquid, water, ice, or wind and become compacted and cemented together. Sedimentary rocks are secondary rocks as they are formed from the accumulation of small pieces of pre-existing rock, that is parent rock. Now there's two main types of sedimentary rocks based on the source of the sediment. Sedimentary rock can form as solid particles from weathered rocks. These particles are called detritus. And detrital sedimentary rocks are accumulations of detritus. Therefore, the source of sediment for detrital sedimentary rocks is weathered rock from another form. For example, particles of sand from other rocks can form sandstone, and mud can form shale, which is the most common form of sedimentary rock. chemical sedimentary rocks are derived from material carried in solution to lakes and oceans. Under certain conditions, the dissolved material precipitates out of solution and thus settles to the bottom. Precipitation may occur due to physical processes such as evaporation or through living organisms. For example, limestone is the most abundant chemical sedimentary rock, and it's typically formed when calcite precipitates due to evaporation. Calcite is produced by living organisms to form shells which can in turn form sedimentary rocks. Now, interestingly, 90% of limestone is of this biological origin. Much like a caterpillar can morph into a beautiful butterfly, rocks can morph into different rocks. Now, in this context, metamorphism is the transformation of one rock into another. Like sedimentary rock, metamorphic rock is a secondary rock. Metamorphic rocks are formed from pre-existing igneous, sedimentary, and even other metamorphic rocks. In short, any rock can become a metamorphic rock. How does this happen? Everything on Earth, including rocks, tends towards what we call a stable state, that is, its lowest energy. Environmental change can cause rock to become unstable. Well, for example, rocks that become buried deep under the earth are under tons of earth and exposed to increased temperature and pressure. And common metamorphic rocks include slate and marble.
Can you name some minerals off the top of your head? You likely came up with things like gold, silver, copper. These are all correct, but there are many more minerals on Earth, over 4,000 in fact. To understand what makes a mineral, we need to understand the basic requirements that categorize them as well as their properties. In order for something to be a mineral, it must first meet 4 criteria. First, all minerals are solid. So while water may contain minerals, water itself can't be a mineral because it's liquid. Minerals are all naturally formed. This means they can't be manufactured in a lab. Synthetic gems like cubic zirconia are therefore not minerals. All minerals have a unique and specific chemical composition. This is like the DNA of the mineral. It's what makes the mineral different from other minerals. Lastly, all minerals have a crystalline structure. Minerals are some of the most beautiful substances on Earth because they are always arranged in an orderly geometric pattern. Minerals of the same type always have the same geometric arrangement of their atoms. Minerals are classified by their chemical composition and crystal structure. These two features occur on a microscopic level, but we can see them in other ways because they determine a mineral's observable physical properties. In other words, what appears to us on the outside is determined by what's on the inside. The 7 physical properties of minerals are crystal form, hardness, fracture or cleavage, luster, color, streak, and density. Let's see how each one helps identify a mineral. Crystal form is the outward expression of the orderly arrangement of atoms inside the mineral. What you are seeing is the actual arrangement and structure of the atoms in that mineral. For example, look at some everyday table salt, which is a combination of sodium and chlorine. Normally, what you see is a salt cube, but if you were to break this cube down into smaller parts, it would simply break into smaller and smaller cubes because that is how the atoms are arranged. Hardness is how resistant a mineral is to scratching, not how easily it breaks. Hardness depends on the bonds within the mineral, so the stronger the bonds, the harder the mineral. Mineral hardness is measured on the Mohs scale of hardness, which compares the hardness of different minerals. Diamond is considered the hardest mineral, so it's a 10 on the Mohs scale of hardness. Talc has a very weak bonds between its atoms, and so it's a 1 on the Mohs scale of hardness. If it helps, you can think of the hardness of talc in relation to the hardness of your fingernail, which is about a 2.5. Fracture and cleavage describe how a mineral breaks. Some minerals break very nicely along smooth planes, and this is called cleavage. Minerals that break this way do so because their atoms are arranged so that they break apart from each other along these planes. Mica is an example of a mineral that has cleavage. If a mineral fractures, it breaks in uneven ways that are not flat or parallel. Again, these minerals break like this because that's how their atoms are arranged. Luster is how reflective a mineral is. Minerals are usually either classified as having metallic luster, which is very shiny or reflective, or non-metallic luster, which is not shiny and is very dull. Some minerals can be identified by their color, but some minerals such as quartz come in many colors. Streak is often a better way to identify a mineral, which is the color that shows up when a mineral is scraped across an unglazed porcelain plate. However, minerals with non-metallic luster all have a white streak, so this is really only helpful for minerals with a metallic luster. Finally, the density is how tightly packed the material of the mineral is. Minerals that are more dense have more tightly packed atoms than those that are less dense. Minerals are in just about everything. That computer you're using is full of them. Do you have any jewelry? All of those stones and the gold or silver that they are made of are minerals. The copper wiring in your house, the nails holding your pictures on the wall? Yep, those are all minerals. Precious stones and gemstones are things that you are likely quite familiar with. They are rubies, diamonds, emeralds, and the like. Metals like gold, silver, copper, lead, iron, zinc are extracted from ore, and the process of extracting these minerals is called metallurgy.
They say that a diamond is a girl's best friend. Rubies, sapphires, and other precious gemstones are also popular ways to impress a lady. Mankind has always been infatuated with rare crystals. Diamonds in particular have become a symbol of love and commitment. Young ladies can't wait to show off when they get a big, shiny rock from the groom-to-be. But should we really be using the word rock to describe a diamond? You may have heard the phrase rocks and minerals at some point in your science schooling. The reason we say rocks and minerals is because they are two different things. Rocks are not minerals, and minerals are not rocks. As we'll soon discover, diamonds are actually minerals. Some people are under the false impression that minerals are things we eat, as in the phrase essential vitamins and minerals. But really, minerals encompass a broad range of natural substances, some of which you eat, some of which you forge into tools, and some of which you give to your future spouse. Let's talk about the differences between rocks and minerals so we can get all our facts straight. We'll start right now with minerals. A mineral is a solid, inorganic, naturally formed substance that has a crystalline structure and specific chemical composition. I know that's a lot to take in, so let's break down this definition piece by piece. First of all, minerals are solid and formed naturally in the earth. Natural solids can be familiar things like sand, granite, salt, and wood. Our definition says that minerals are inorganic, which means that they do not consist of tissues from living things. So that means that wood is not a mineral. It also says that minerals have a crystalline structure. That means that the component atoms of the substance have a repeating three-dimensional arrangement. This is a picture showing how the atoms of salt are arranged. Salt is also called sodium chloride because it's made of two types of atoms, sodium and chlorine. The sodium and chlorine atoms are put together in a very specific three-dimensional lattice that repeats over and over until you get to the end of the salt crystal. Yes, it's a crystal. I know you typically don't think of salt as being a crystal, but it is, and so is sand. Sand is just tiny chunks of quartz crystal made by a pattern of silicon and oxygen atoms. What about our last substance, granite? It's solid, it's formed naturally in the earth, it's inorganic. But does it have a specific chemical composition? Does it have a regular, repeating atomic arrangement? No. Granite may be made up of minerals, but it's not a mineral itself. It's a rock. A rock is a solid, inorganic, naturally formed substance without a particular atomic structure or chemical composition. It's probably easier to just remember that rocks are made up of two or more minerals. Examples of rocks include granite, limestone, marble, pumice, obsidian, sandstone, shale, and slate. Each of these rocks consists of several different minerals, which are mixed up inside the rock through a variety of geologic processes. Let's take granite for example. Granite is mostly composed of 3 minerals, quartz, feldspar, and mica. Each of these minerals can be found alone in nature, but here they are mixed up inside of the rock. Sometimes you see large chunks of one of these minerals inside of the granite, but when you take the stone as a whole, you have to call it a rock. Other rocks are much finer grained than granite, so it's not easy to spot the different minerals. Slate is a rock that was made from clay, and clay is composed of tiny, tiny particles. Those particles can be minerals like quartz, pyrite, apatite, muscovite, feldspar, kaolinite, biotite, tourmaline, the list goes on. But you can't see these minerals inside of a slate rock. The slate looks all the same color and texture. Still, it's not a mineral because it has no regular atomic structure or chemical composition. Rocks are made of minerals, and minerals stand alone. Another way to distinguish between rocks and minerals is by their classification systems. It makes sense that they would be classified differently since they're different things, but many students get confused. They try to describe a rock as though it were a mineral, or describe a mineral as though it were a rock. At the most basic level, rocks are classified by the geologic processes that form them. The 3 main groups are igneous, metamorphic, and sedimentary rocks. Minerals are not classified this way. You can't say that quartz is igneous because it's not even a rock. Minerals are classified by their properties and chemical classes. Chemical classes of minerals include groups like silicates, sulfates, and carbonates. We group the minerals based on the atoms and chemical bonds that make them up. Silicates include minerals like mica and feldspar. Carbonates include calcite and dolomite. Some minerals, called the native elements, have only one type of atom. These include copper, gold, and silver minerals. Scientists also classify minerals by their properties, like density, hardness, color, fracture, luster, cleavage, and crystal habit. Crystal habit describes the way minerals form 3-dimensional shapes based on their atomic structure. You may know that carbon atoms make up the fragile mineral graphite. Graphite is used in pencils because it is so soft it makes an excellent substance for marking on paper. Graphite can shed off pieces of itself because its carbon atoms are arranged in parallel sheets. These sheets of connected atoms slide off from each other and allow us to mark our paper with the mineral graphite. But carbon atoms can be arranged in a completely different way, a sturdy, 3-dimensional lattice that is nearly impossible to cut or break. This form of the carbon mineral is called diamond. It's composed of exactly the same atoms as graphite, but because of its crystal structure, it's the most durable and indestructible gemstone of all. It is this durability that inspires us to use diamonds as a symbol of love and commitment. So next time you're admiring diamonds at the jewelry store, be careful not to call them rocks. Instead, you should call them carbon-based minerals with a 3D atomic lattice. That will really impress your husband or wife-to-be.
Fool's gold is an expression used to describe the mineral pyrite, sometimes called iron pyrite. The name fool's gold comes from when novice gold prospectors mistook tiny pieces of pyrite for gold when panning for it during old mining days. However, on close inspection, the mineral really looks nothing like gold, and I suppose that's why they were considered fools. Pyrite is a metallic mineral that is composed of iron and sulfur atoms bound together in a ratio of 1 iron to 2 sulfur, and it is arguably the most abundant sulfide mineral on Earth. The name pyrite comes from pyrite lithos, which in Greek means stone which strikes fire, in reference to the tendency of the mineral to spark when struck against steel. In fact, pyrite was used for that purpose in early flintlock rifles. The mineral is found in many sedimentary rocks such as limestone, shale, and coal, as well as in metamorphic rocks like schist. It is a very common mineral in ore deposits, where it is found along with other metal-containing minerals, including gold, and yet pyrite is not mined for its iron, as the metal is difficult to extract from it. In some rocks, usually shale, pyrite forms pyritized fossils, where the pyrite replaces shell material inside the fossil. An example of pyritized fossil is shown in this picture of a cephalopod fossil. Pyrite rates a hardness of 6 to 6.5 on Mohs hardness scale, the scale used by geologists to describe a mineral's resistance to being scratched. For comparison, quartz has a hardness of 7, diamond has a hardness of 10, and gold has a hardness of 2.5. Pyrite has a brassy yellow color, but it does not look as bright yellow as gold. It also sometimes displays greenish-black streaks. If pyrite is ground into a powder, its color appears greenish-black, while powdered gold is still yellow. Pyrite crystallizes from iron and sulfur-bearing water solutions, sometimes heated, in which there is very little free oxygen. In chemistry, that's known as reducing environment. Bacteria may also be found in some pyrite deposits, particularly in shale. When the mineral forms crystals, they can assume a number of possible shapes. One common form is a cube with 6 square faces, as shown in this picture of pyrite crystals in schist. Another form is an octahedron, which has 8 triangular faces. A common form is the pyritohedron, a 12-sided crystal named after the mineral pyrite. Each pyritohedron has 12 pentagonal faces, as depicted in this picture. Pyrite can also form combinations of these shapes or lack any visible crystal forms and occur as irregular grains spread out through a rock. Pyrite can also fill in gaps in shale layers to form radiating growths called pyrite suns or pyrite dollars, as shown in this picture. Whether in crystal or massive form, pyrite has a metallic luster. However, because the mineral does react chemically in air, it often has a dull or tarnished appearance. Because pyrite is often found near gold, gold atoms can substitute for the iron atoms in pyrite's atomic structure. Accordingly, some gold deposits do contain pyrite that contains several tenths of a % of gold in it. That likely is the source of the confusion between the two. However, it hardly makes pyrite as valuable as pure gold. Nickel also substitutes in the structure, forming a closely related sulfide mineral called bravoite. When pyrite-bearing rocks are exposed to the elements, the mineral reacts readily with oxygen and water to form new iron oxide and sulfate minerals, as well as sulfuric acid. That chemical reaction causes the acid mine drainage that is a common problem in mining regions, including metal and coal mines. An example of acid mine drainage is shown here. The iron oxidizes in the water, not the sulfuric acid, are what color the drainage orange. On the other hand, that same chemical reaction has been used in commercial-scale sulfuric acid production since the 15th century. Pyrite is also used to make sulfur dioxide, which is used to bleach paper and in other industrial applications. Some of you may own marcasite jewelry. It is actually pyrite that has been cut or faceted and polished. Just to confuse matters, the jewelry shares the same name of another iron sulfide mineral, similar to pyrite, that is not used for jewelry because it oxidizes more quickly than pyrite. Maybe fool's marcasite is a better name.
So don't forget, if you have any live questions later on, if you go back to listen to the videos and you have other questions, just send them over and I'll try to answer them better, as best as I can. Don't seem to be any questions so far. So thanks for your participation and see you for the next lesson, which will be in 2 weeks. And it will be about, this time we'll be talking about the rocks deformation. So everything that has to do with structures and one part of what we just talked about is transformation on the rocks based on their temperature and pressure. So everything that changes from alteration and physical transformation. So to be followed. Thank you.